Hello and welcome. My name is Keno Kelly, and I'm here today to talk to you about IEEE 802.11w denial of service attacks, as well as some general security concepts when it comes to 802.11. So first today we'll start by talking about a review of the 802.11 protocol as previously discussed in lecture. We'll skim over some of the denial of service and other security issues with 802.11. And then we'll talk about what 802.11w brings to the table and how it attempts to fix some of these issues. And then we'll look at the problems with this implementation and see if we can exploit any of the vulnerabilities. So first of all, 802.11 is the wireless communication standard that was first ratified in 1997. The first security implementation was WEP, which was known to be very, very insecure, and was replaced in 2004 by 802.11i, which defines what we know as WPA2. WPA2 uses AES block cipher, of course, to encrypt the traffic, and it uses either a pre-shared key or EAP exchange with the 802.1x. And so during the authentication, both sides prove that they have shared knowledge of the pre-shared key by using a four-way handshake, never actually transmitting the key. And in this protocol there are management frames which are to manage the network state, and these include things like authentication, deauthentication, association, disassociation, beacon frames which announce the network is there basically, and probe requests and responses. There are also control frames that manage transmission behavior in some cases when these features are used. So taking a quick look here at this diagram on the left, we can see the state machine used by a typical access point. So state 1 frames are sent by a station when it is not authenticated nor associated. And a typical state 1 frame would be an authentication request. The AP receives this request, sends back a successful response, and then moves that station to state 2, which is authenticated but not associated. Then the station has to send an association request and successfully associate. The AP will send back a response. Then it will be in state 3, which is both authenticated and associated. And then it can do a handshake or whatever else it needs to do at that point. On the right, we have a diagram of how the four-way handshake works for WPA2. So the access point starts out by sending the first message, and they exchange messages until the last one. And then at that point, the encrypted connection is complete and ready to go. So some of the problems we see, even with 802.11i in place, is that there's very little control over who can send management frames. So anybody who knows what they're doing is capable of forging a management frame to cause a deauthentication, to forge authentication, or to pretend to be an access point using beacon frames, or pretending to be a client by sending out probes. So here we will observe a traditional deauthentication attack against a typical 802.11 network without protected management frames. So on the top left you'll see the host is currently pinging the gateway, which is working at the time. However, once we start running the tool on the right hand side, the pings will fall off, and the bottom left, which is showing the output of WPA supplicant, will start to show deauthentication messages coming in. And so this is pretty concerning. It means that anybody can pretend to be the access point and deauthenticate all the clients that are connected to it. Additionally, control frames do not require any authentication at all, and we'll get into this later a bit. But we have these frames that essentially allow you to reserve time on the air, and if they're abused, it could be used to prevent anyone from transmitting. So the consequence of these management frames being unprotected is that anyone can kick devices off the network or create a deadlock, creating a denial of service. So why does this matter when jamming attacks still exist? Well, MAC layer attacks are generally easier to carry out, they're harder to physically track down, and they may be persistent once launched. So it's possible that someone could send a single packet which would crash a device on the network, and that is more likely with a MAC layer attack than a physical layer attack. And wireless attacks are a big deal anywhere that wireless technologies are used. You could take down an entire network at a business or even something that affects critical infrastructure. So there are clearly some problems with the management frames being unprotected in 802.11. So let's look at what 802.11w brings to the table, or at least what it tries to bring to the table. So 802.11w introduces protected management frames, or PMFs, and a protected management frame is essentially a management frame that is encrypted using the key like any other data is over a WPA2 network. So this means that any deauthentication or disassociation frames must be encrypted with that key, just like any other data. Otherwise, the client or access point will ignore them if they're not properly protected. So this solves all of our problems, right? False. So as you may have noticed, a couple slides back, there were several things that we noted as not protected under 802.11. Really, of the things we care about, it only covers the deauthentication and disassociation packets. There are still several other kinds of packets that can be sent without authentication. In addition to this, the added complexity of 802.11w introduces new cases for the access point and the station to become desynchronized, such that a deadlock is caused and neither one can communicate with the other. An example of this, going back to the state diagram, would be when the access point and station are in stage 3, and a request is sent to the access point demoting the station to stage 2. However, the station does not know it has been demoted to stage 2 and can no longer communicate since the access point has deleted its keys. So the consequence of this, of 802.11w not fully protecting everything, is that the above frame types and potentially other attacks can still be carried out by anybody even if they do not know the network key, causing denial of service. So looking for uses of 802.11 in the wild, not very many products actually use 802.11w. There are some enterprise products, notably by Cisco, that use protected management frames. However, it's not very mainstream, especially on consumer wireless hardware. Modern operating systems should support use of 802.11w, and so should hardware. Even on custom firmware builds such as DDWRT, support for 802.11w is fairly thin. It usually requires someone to rebuild the firmware from scratch in order to enable the 802.11w option in host APD. So the goals of this particular project are to examine the state of 802.11w security on modern components. One of the main parts is to validate and or disprove previously researched attacks in my setup, and in general learn more about 802.11 denial of service attacks in order to better understand what should be done in the future to avoid those sorts of attacks. And lastly, to develop a tool to automate attacks against 802.11 and 802.11w. So in my test environment, I performed several tests to try to verify some of the vulnerabilities that were described in some research papers. Most of the vulnerabilities were confirmed working by the paper authors. However, there was limited evidence and no source code provided to verify this, so I went on to implement these attacks myself. Do be aware that the outcome of these tests is heavily influenced by my particular setup, and may have different results depending on particular implementations of various products. That is to say, some attacks that do not work here may work in different environments, and vice versa. In the environment is an access point, a client, an attacker, and a monitoring station. Each of these different components has their own wireless adapter. The wireless adapter for the access point, of course, is in master mode, the client is in managed mode, and the attacker and monitor are both in monitor mode. For the access point, the open source access point software, host APD, was used, the most current version, which was 2.6 or 2.7 when built from source. And on the client side, WPA Supplicant, which is an open source and cross-platform supplicant, was used to connect to the networks. So one of the first attacks we'll look at here is something I briefly mentioned earlier, but it's an attack with authentication. This attack is against a client that is already connected to the network. This attack is possible because in order to avoid deadlocks, the access point must allow a station to try to reconnect to the network in case it loses its keys. For example, if the machine was force powered off and it lost its WPA2 keys, it'll have to renegotiate the connection with the access point and will not be aware of the previous key in the previous state. Hence, it will not be able to send a protected deauthentication frame. So it must be able to send an open authentication request. And that's what the attacker can do here. If they send an open system authentication request, the access point believes that the state of the client has changed, it has forgotten its keys, and is trying to reconnect. When the client tries to send more encrypted data, the access point notices the discrepancy in state and sends a disassociation. This forces the client to delete its own keys and try to reassociate again. This can be repeated by the attacker to ensure that the client cannot reconnect. However, in practice, this attack did not seem feasible. The current version of Host APD did not behave as expected by this research experiment. In fact, Host APD took no action whatsoever when it received the authentication request. Looking at the source code of the Host APD, it was determined that it would not attempt to delete the keys of the client just from an authentication request if protected management frames were in use. However, against an access point without 802.11w, this attack was determined to be effective with a Host APD. However, against an access point without 802.11w, this attack was very successful. It caused the AP to believe the client was in a different state than it was actually in, and did not inform it of this change of state. So the client is sitting there trying to send data, whereas the access point is complaining because the client is not associated anymore. This caused the client and access point to sit in a deadlock for several minutes until the access point's activity timer ran out and sent a forced association request to the client. In a way, this attack was more effective than a traditional DAuth attack because it persisted and only took one frame to be sent. This is a demonstration of the authentication attack. The moment the attacking host starts sending the authentication requests, the pings stop responding, and the access point no longer will talk to the client anymore. A second attack abuses a race condition in the four-way handshake. As mentioned earlier, before the four-way handshake is completed, all communication between station and access point is unencrypted, so the attacker can see the entire four-way handshake and interfere with it as it's going on. So if the access point or station receives a deauthentication request during the ePOL handshake, it may cause the access point or the client to abandon that attempt and try to start over. However, a notable attack can be caused by exploiting a race condition after the third message, because at this point, the access point has sent message 3 of 4, and the station will believe that it has completed the process at this point, and it will send back its fourth message. Now, if the attacker manages to send a deauthentication from the station to the access point before message 4 reaches the access point, it'll desynchronize the state of both the client and the access point, such that a deadlock may occur. Now, in reality, however, this attack proved harder than expected to actually execute. Part of the problem was the speed at which it was possible to first identify the ePOL message 3 and respond with a deauthentication. Perhaps in the original experiment, conditions were more ideal to this, or the code was faster. By the time the access point received the deauthentication, it had displayed an error message complaining that it received an unprotected deauthentication request. However, it may be possible to cause denial of service by spamming large numbers of deauthentication all the time, so that if a client does try to authenticate, it'll hit the access point during the handshake or before the handshake and invalidate that state, causing the client and the access point to try again. Additionally, even if the race condition was possible to pull off in my scenario, WPA supplicant implements the optional 802.11w deadlock recovery protocol and would have been able to get itself out of that situation. A third attack against 802.11w exploits control frames, which are also not encrypted. So CTS, RTS, which is request to send, clear to send, is a protocol that can be used partially for compatibility with 802.11b devices, but more importantly when a device is trying to communicate to a second device and is unaware of a third device that's also transmitting at the same time. CTS and RTS can help them communicate and know when to talk. So any device that wants to transmit over a set threshold, which is usually below 2347 bytes, they must send a request to send. once it is the client's turn to transmit, the access point will send a clear to send frame addressed to it, containing a duration that they may transmit for. However, this opens up an attack. If you look at the structure of the CTS frame, you'll notice there is only a receiver address. And so all an attacker has to do is spam a lot of these messages with a non-existent receiver address. And all devices on that current channel, so not just the target access point or target network, they will be forced to wait before they can send their frames, potentially causing complete slowdown of the network. Unfortunately, I was not able to set up a network that was fully working with CTS RTS in order to test this, but the functionality is implemented. Another attack abuses the dynamic frequency switching component of 802.11h, also known as DFS. This feature is intended for 5 GHz networks to switch channels if they detect radar, which is usually from a military installation, such that they don't interfere with it. This is only required on 5 GHz networks. However, many stations seem to implement this feature on 2.4 GHz as well. And most importantly, the channel switching announcement is not sent in a special management frame. It is sent in an ordinary beacon frame, which is not covered at all by 802.11w and is therefore not protected. This attack is very effective on 802.11w and regular 802.11 networks, but it only works when the client respects this protocol. And this is an example of the dynamic frequency switching attack. On the bottom right, you'll see that the current channel of the client interface is being printed out. The network's on channel 1, but the attack will move the client to channel 9, thus breaking their connection. In addition to the attacks that were implemented, several others are detailed that may be successful as well. Another one of these attacks abuses the EPOL handshake. It waits for the access point to send the first handshake message, and then repeatedly sends similar forged messages to their client to force the client to keep generating the new PTK instead of proceeding to the next step. Additionally, SA query manipulation can be used to create a deadlock in some scenarios. SA queries are used by an access point when the access point receives an unprotected frame from a client it believes should be authenticated already. It will send out an encrypted SA query to challenge the device if it still is online and authenticated to respond. If it does not respond, then it knows the device has actually been disconnected and can begin steps for reauthentication. When the access point asks the client to solve the challenge, the adversary can construct a similar message to the client, including a timeout value. This timeout value can be made longer than what the access point expects, and this will cause the client to never respond in time, causing the access point to invalidate the SA and delete that key, causing the client to become disassociated without its knowledge. Then the client will respond with the valid challenge response, but the access point has already deleted the keys and will not be able to decrypt it, then deauthenticating the client, which may lead to a deadlock. So in order to solve these problems that are existent in both 802.11 and 802.11w, new steps need to be taken. So first of all, control frames should be encrypted to prevent an attacker from arbitrarily sending out clear to send requests. The caveat with this is that control to send is supposed to work across multiple networks, so some standard would have to be established to allow separate networks to still communicate in this way without the potential of denial of service. Additionally, deadlock detection should be implemented on both access point and client to ensure that no invalid states can be reached. Lastly, most of the problems are solved by protecting the authentication frames. Some methods for doing this include establishing a temporary tunnel using asymmetric cryptography, or by creating separate subtypes for key management and authentication frames. This way, the EPOL messages can be encapsulated inside other subtypes and protected by 802.11w. The plus side of the temporary tunnel is that traditional attacks that involve brute forcing the PSK are no longer possible since the entire handshake is carried out over another encrypted channel. So as part of this project, I developed some code in Python that automatically executes some of the attacks. This code is hosted on GitHub and is completely open source. It makes heavy use of the SCAPI packet manipulation library to perform the attacks. Let's take a quick look at the tool in interactive mode. When run from the command line, the tool will first start out by printing out the list of access points in the area as it scans all channels. The ones that support 802.11w are highlighted in magenta. An access point and client may be chosen to carry an attack out against. Although note that in some cases the attacks apply to all clients on that network. In this case, the channel hop attack is being used again, and this will target all of the clients on the network. And as before, that attack is successful in taking down that client's connection.